This one is about programming models, programmability in general, efficiency related to programmability, actually. So it's not an ML talk. And the topic here is that this is a collaboration we have, Total Energies, with Stony Brook University, the team led by Barbara Chapman. So Buddy, the main author of this work, is a PhD student supervised by Barbara and working with me on this topic. So the topic, since Barbara Chapman is included in this, is something about OpenMP. Programming model, well-known programming model, ubiquitous, present in most HPC tools in some shape or form. And basically, we want to explore new features in OpenMP and see how they can help us with our programs, HPC programs. So I have the legal blah blah that I have to do every time, like everybody else, for some seconds. Basically means don't take any of this to make decisions of investments and blah blah blah. Obviously not from this talk, but you know. Anyway, let's go. So summary. This is in the context of LLVM Clang. We have a branch of LLVM, of the OpenMP part of an LLVM, where we are trying to explore on these new topics. And recently, offloading has been quite in the news on HPC because of interesting opportunities to do some things that weren't possible before with OpenMP and especially for heterogeneous computing, right? OpenMP started very homogeneous shared systems, basically shared memory systems, but adding target and offloading expand that to all kind of hardware. So that really helps, and I'm going to show how that helps us. Then we have the traditional approach, which is MPI plus OpenMP. Well, some people do MPI plus CUDA or MPI plus OpenACC. More general OpenMP, because actually OpenMP can sort of take over the others to a certain extent. Then we were thinking, can we do OpenMP OpenMP? That's the actual thing, that kind of a dream, if you imagine that. Just programming serial, then adding OpenMP decorations, and good luck, you get the thread level and the distributed level at once with one runtime. That's kind of the dream. So I remember this morning, Messer, I don't know if he's here, he was talking about why MPI cannot be replaced. Maybe because he said the conditions that you have to be ubiquitous runtime industrial support, that's OpenMP. So I don't know, I'm just putting it out there. And then some results. So that's what we got. Okay, so for people not familiar with OpenMP on what I'm talking about, so let's say we have this very simple computation and serial fashion, and then adding just this pragma here. Now this piece of code can be computed, and any target that I design can be Intel GPU, AMD GPU, x86, ARM, you name it, and then adding some extra decorations to it or conditionals, you can have this parallel and distributed, right? So it's okay, now I can run this everywhere basically from just adding this and not to do all the other stuff you usually do. So we are really interested to get to this some way or another, and that's basically the tip or the objective of this work. So you can compile this with Clang and use the proper target. You define at this point this is for run on CUDA and NVIDIA GPUs, but you can replace the target with any of these guys. If you want to know more about this, the specification right now it's at 5.2, I believe, or 5.3, and this is part of the specification, so you can actually do some of this in some compilers, because remember, OpenMP is only an industrial standard. OpenMP does not implement these things. The things are implemented through specific compilers or frameworks. In this case, it's Clang, right? But you can use others. Most of major compilers support at least up to 5.0 OpenMP features. Okay, so like I said before, this is the traditional scenario for most distributed codes in the industry. You will have an OpenMP distributed runtime doing the work of sending chunks of work to different nodes. And then within the nodes, you will have either OpenMP, CUDA, or whatever you are using for lower level parallelism. So you have a hierarchical situation, two runtime working together, and then actually the work being done at the device level, right? So this is by default, by the book, I will say, these days. So what we want to do is something more like this, when it's only one runtime taking over and doing the whole work. The reasons, like I said before, simplicity, programmability, portability, and so on. A lot less tricks that you need to know to get the thing actually working fast and properly for you. So how that works, you have your code, and then you have to, when you are compiling linking, you're linking against these different libraries and plugins, up to when you, if this is for an NVIDIA GPU, you will call the CUDA RTL that is then instantiated here, and so on, right? But here, that's the additional way, but here is when we inject something specific, which is target and offloading. So the target part is not really new. It has been there in 4.5 or something in OpenMP. It just basically means that the backend that is going to actually execute the code, it's any of the one I presented before, all kind of hardware at this point out. The new part really is the offloading part, which is, okay, now I'm going to be able to send work remotely to another node, right? So there's something like a client-server situation, but all run by the OpenMP runtime, where I have chunks for my local GPUs, but I can also offload to other nodes' GPUs. So that was the beginning of starting to distribute pieces of work using OpenMP. That was presented or introduced last year, so it's quite new, by Derfert and Patel at the ISC. And actually, this paper won the Best Paper Award at ISC last year. And that shows you how this is quite interesting to the community, if this is possible to do in an efficient fashion. So we took it from there. We are in contact with Johannes. He's in the OpenMP LLVM lead for Seyen. And so we fork basically what he was doing, and we start adding some other things. And that's what I'm going to show next. So basically we changed the serializer path, we add some CUDA-aware for the codes that run in CUDA, we add some locality. So we create a new plugin that has all these things. So it goes here, right? It's injecting all these things here. And we present those results in the IWOP last year. So that's September. So just after Johannes put out the first brick, we put some other bricks on top already that can make this more efficient. But that wasn't all. To this point, the key part here is the communication, the layer that is going to be doing the offloading. And so far, what Johannes and to this point was using is UCX as a layer. And we thought, okay, UCX has some good things, but other not so good things. So let's see if we can do something different. And that's what we did later. So here's the irony of the thing. We actually decided to use the MPI layer as the communication layer, but not the MPI runtime. So we are doing this abusing of MPI protocols just for simplicity. And then we are able to do this, right? So now it's an MPI remote layer that we create. So we went from the UCX one to the MPI one. That was the first thing we did. And the nice thing about that is that then we can basically overload MPI scripts to start this process, right? So we use srun, but it's actually not running MPI at all. It's running OpenMP that is using the MPI as a communication layer. And you see this really simplifies the previous version, the original version that used UCX, where you had to define everything explicitly. Here is much more comprised, and everybody is familiar with MPI plus X paradigm is familiar with how to use this. So we piggyback on that, and we add this new to the plugin that we decided. And then we start to do other things. Like, okay, since we're using the communication layers of MPI, we can do all these things where we have locality and targeting of the memory transactions and stuff like that. So the old version to do this was something like you need this decorator and then the other decorator to say, okay, I'm sending this chunk from this place to the other place to the runtime. Now we just create this one, and this one knows the beginning and the end of the different communications and so on. And this one is the latest iteration of this plugin. So this is actually being presented right now at the PPOPP conference in Montreal. So Baudi is presenting this there, and I'm doing it here. So it's quite interesting. And yeah, so you see this work, this effort is getting attention. People want to see what else can be done, how they simplify your life, and that's kind of the objective. So performance, obviously. So let's take some results. So this is map. So it's synthetic. You're moving just data around and try to measure latency for different sizes of messages, right? So you have the baseline, which is the UCX original Johannes version plugin. Then we have when we optimize it, we call it opt. And then the new is the one that uses a different transport layer, which is the MPI actually layer. So different colors, you can see the performance lower better. So the new one actually does very well. This was a kind of surprise because UCS's strong selling point is latency. But looks like with this one we can do actually better. That was interesting. And this is the to and the from, so the two sides of the communication, lower better again. And again, we are pretty much good at really outperforming the previous version for small sizes, and then it gets more closer to what the others can do for bigger communication. But for a proof of concept, this is quite acceptable. In case you're wondering, this is in our system here in Houston. So we have like Mellanox InfiniBand network. So network is not really a problem here for these experiments. This one, this is different. This is XSBench. So here we have actually some multiple resources at work, right? So this is the configuration, one node for GPUs, two nodes and GPUs, and so on. Lower better, a small size of setup problem, and larger. And again, the new version, the new, it's okay. For the largest, especially, it's a lot better. We are still investigating why this happened here. This is really out of the oven. This is really new results. We are not fully through the data yet. So we got this. But the good thing about this is that these are for large message, and that's where we live. We really live more here than here. So this is great for us. As a result, this is the setup for the hardware. If you're wondering what's the resource underneath, it says host is AMD, and the GPUs are NVIDIA 100s to compute the XBench. So also good. All the synthetics looking good. We are competitive against the traditional way of doing, or the original, at least the original plugin of doing this. So then let's see what's the gain. Well, these two things do the same now. So this is the MPI version, where you have to define all these things to finally get to a place where you can actually execute the loop, right? Here's the loop, and here are the decorations you need. This is the USX version, so the original Johannes version. So it's OpenMP OpenMP. Offloading, not fully distributed yet, but this is all what you need, and then you're running. So that's the game here. That's what we want. We want people that are not HPC experts, that are going to not spend a lot of hours optimizing or knowing all the details of OpenMP to get something that is distributed and get some relatively good performance. So I have 3 minutes, and I got to go to our thing, which is, the seismic stuff. So this is for modeling. We have domain decomposition. So this is the US that I showed before. This is the new transport using OpenMP MPI. So you see that the decorations are even simpler now with the MPI version of it. And yeah, it works. In terms of performance though is not as I would like it to be honest. So this is the reference solving the problem. Problem sizes, these are cubic size domains that we are solving for a seismic modeling problem that we port. You see different sizes. The bigger one is this one, the red one, which is the most of interest to us. And you see that the scalability is the best for that one. But this scalability is not really what it should be. This should be like this, okay? And obviously, after certain configurations, they start to drop back. So this is all on us. We have to make this plugin more efficient, obviously, and we are investigating why this is happening. But as a proof of concept, we actually are winning, and with a lot less complicated piece of software, maintainability and portability and so on included, right? A little bit of profiling. So here, quick view of this. If you have white spaces, that's bad, basically, right? Because blue is computing on the GPUs, and red is I/O or communication. The whites are runtime blockage. That's some kind. That's on us, and that's the parts that we need to improve to make this really competitive. When this is producing results that are on my taste, then we're going to push this in the main branch of LLVM, and you can give it a shot and your different places of work. So basically, yes, maybe we have an opportunity to do something simpler than MPI that still give us performance with a lot better portability and programmability. We think that OpenMP is the right place to do that since it's ubiquitous and used by many, many people and teach at actually universities and so on. And the things that will come about this work is we want to look at maybe instead of using MPI as a transport layer, going for PGAS or more one-sided oriented communication. This one is already implemented. The results were like last week, so I didn't have time to really. And then there are a couple of other things we might think about. Tasking, that is also another way of doing this. We already have an implementation for this one too, much more flexible than structured domain decomposition or static domain decomposition. So we are thinking about these topics too, and that's what I got. Thank you.
All right, thank you, Mauricio. We have time for a minute or two of questions. Anybody have any questions for Mauricio? Yes. I'm going to go to the one I can reach first over here.
Hi, great talk, thank you. Really nice to see that clean, simple code. I was curious, so a lot of your benchmarks are kind of comparing against the old and new implementation. Do you have like an ideal, kind of like optimized version of the code, say you're using MPI right now that you have in your benchmarks too that you're trying to strive towards?
For the seismic code, yes, because we have the old one, right? And the old one, MPI plus CUDA, scales linearly up to 32 GPUs for that problem sizes, right? This one, as you see, at 8 GPUs, start to drop. So that's what I said. That's on us. We have to make it better. When it's competitive at that level, then it's going out. But for the first step, it's pretty good, I think.
Yeah, it looks nice. Thank you.
Hey, Maurice, one question. Think you can achieve overlap of communication and computation using this approach?
Yeah, so we didn't try that yet because of the limitations to a certain extent of our plugin. So it's against on us. But yeah, that's it's out there, right? And for Fraunhofer, I think this is also interesting because it's OpenMP, and you guys are OpenMP chopped, so you would like to use this for STX or any other hardware of your choosing. Yeah. Thank you.
All right, thank you again, Mauricio. That's great.